Hello everyone, welcome to the lecture series on kinematic analysis of mechanisms using analytical methods. Under this, in today's lecture, we will discuss about kinematic analysis of Hooke's joint. First of all, let us see the characteristics of single Hooke's joint. This is a single Hooke's joint. Now, single Hooke's joint is used to connect two non-parallel intersecting axis shafts. So this is the input shaft and this is the output shaft. Input shaft is connected with a fork at its one end, as well as output shaft is also connected with a fork at its one end. Both these forks of input and output shafts are joined using a centerpiece which is in the form of a cross. Arms of the centerpiece, which are perpendicular to each other, rest in the bearings of the forks of both the input and output shafts. Now, let us suppose that the input shaft rotates with the speed of omega 1 radian per second and the output shaft rotates with the speed of omega 2 radian per second. Now, the characteristics of single Hooke's joint is that speed of input shaft is uniform, that is, input shaft rotates with uniform speed, but the output shaft rotates with continuously varying speed. Okay, so omega 1 is constant and omega 2 is varying continuously. Even though the speed of output shaft is varying continuously, both the shaft completes one revolution in same amount of time. So we can conclude that mean speed of output shaft is equals to the speed of the input shaft, because both the shafts complete one revolution in same amount of time. So consider the shaft 1 with fork ends AB. Now when the shaft 1 is rotated, fork ends AB will move along a circular path as shown in the top view. Now let us consider the shaft 2, which is connected to shaft 1, and shaft 2 is having an inclination of alpha with the shaft 1. Now as seen along the axis of shaft 1, when shaft 2 rotates, the fork ends C and D will traverse an elliptical path. Now let us suppose that the input shaft 1 is displaced through an angular displacement of theta in the direction shown. Now as seen along the axis of shaft 1, angular displacement of fork AB will be theta, as well as it will appear that fork CD of shaft 2 has displaced by an same amount of angle theta along the elliptical path. But the true angle turned by the shaft 2 is different than the theta. The true angle turned by shaft 2 will be viewed along its own axis. That is, when we see the rotation of the fork CD along the axis of shaft 2, we will see that CD is actually traversing a circular path, and the angular displacement of fork CD will be different than that of theta. So to get the actual displacement of fork CD, we project point M on ellipse on the true circle. So we'll project the point on fork CD, then on the diameter AB, and back to the true circle. So angle phi will give the true angle turned by the shaft 2. So doing a little bit trigonometry with these two triangles, including angle theta and phi, we get relation between angular displacement of input and output shafts in this form. Tan of theta equals to cos of alpha into tan of phi. Now this is the first equation which defines the input angle theta in terms of output angle phi. Alpha is the angle of intersection of axis of both the shafts. Now after differentiating this equation number 1 with respect to time, we get angular velocity ratio equation, which is omega 2 by omega 1, that is speed of driven shaft divided by speed of driving shaft, is equals to cos of alpha divided by 1 minus sin square alpha into cos square theta. Now for equal speeds of both the shafts, omega 2 becomes equals to omega 1, so this velocity ratio will be unity. So substituting omega 2 by omega 1 is equals to 1, we can find out the condition for equal speeds of both the shafts. So by putting omega 2 upon omega 1 is equals to 1 in this equation, we get the relation between the angular displacement of input shaft and the angular misalignment between both the shafts, alpha, which is tan of theta is equals to plus minus root of cos of alpha. So for equal speeds, tan of theta is equals to plus minus root of cos of alpha. So this equation will give you the values of angular displacement of the input shaft theta, at which the speeds of both the shafts become equal. And we get 4 values of theta for equal speeds of both the shafts. By solving this equation, 2 values corresponds to the positive sign and 2 values corresponds to the negative sign. That means during one revolution, the speeds of both the shafts become equal 4 times. Now since the speed of output shaft is varying, it must vary between its minimum and maximum values. From the equation of angular velocity ratio, we can find out the maximum and minimum speeds of the driven shaft. Omega 1 is constant, so for omega 2 to be maximum, right hand side of this equation should be maximum. Now again in the right hand side, alpha is constant, so cos of alpha will remain same or constant. Now for right hand side to be maximum, since numerator is constant, denominator should be minimum. All of this whole term in the denominator should be minimum, and for denominator should be minimum, which is 1 minus this term. The 1 minus this term is, in this term alpha is constant, so sin square alpha will remain same. So 1 minus sin square alpha cos square theta, to be minimum, cos of theta should be maximum, and this will happen for theta is equals to 0 degrees or 180 degrees. So we can say that angular speed of output shaft, that is omega 2, is maximum when input shaft has turned through an angle of 0 degrees and 180 degrees. So by substituting theta as 0 or 180, we will get omega 2 max is equals to omega 1 upon cos of alpha as the maximum speed of the driven shaft. So which happens at theta equals to 0 and 180 degrees. Similarly, for omega 2 to be minimum, numerator is constant, denominator should be maximum. For denominator should be maximum, cos of theta should be minimum, and cos of theta is minimum when theta is equals to 90 or 270 degrees, because cos of 90 is 0. So numerator will be such that it will give minimum speed of the output shaft, so which is equals to omega 1 into cos of alpha. This is obtained by substituting theta as 90 degrees or 270 degrees. 90 degrees or 270 degrees. So minimum speed of driven shaft is obtained at the angular displacement of input shaft for 90 and 270 degrees, and this value omega 2 minimum is equals to omega 1 into cos of alpha at 90 and 270 degrees of rotation of input shaft. So you remember this equation. Maximum value of output shaft is omega 1, that is the speed of input shaft, divided by cos of alpha, and minimum value of output shaft is equals to omega 1, that is speed of input shaft, into cos of alpha. Now we can represent the speeds of input and output shaft using a graphical diagram called as polar diagram. And this, since the speed of input shaft is constant, we can take omega 1 as the radius of circle and draw a circle representing the speed of input shaft. Now the speed of output shaft is varying. We know that its maximum value occurs at theta equals to 0 and 180 degrees. So we get these 2 points along the horizontal axis, and the minimum speeds of output shaft occurs at theta equals to 90 and 270 degrees. So we get these 2 points on vertical axis. So when we join these 4 points, we get an ellipse. So ellipse represent the speed of the driven shaft, which is varying. Now semi-major axis of this ellipse will be the magnitude of maximum velocity of the driven shaft. We know that maximum velocity of driven shaft is equals to omega 1 upon cos of alpha. So value of omega 1 upon cos of alpha is the semi-major axis of this ellipse. Similarly, semi-minor axis of this ellipse defines the minimum speed of driven shaft, which is equals to omega 1 into cos of alpha. Now you can see both these curves intersect at 4 points. That means speeds of both the shafts become equal at these 4 points, or 4 times in one revolution speeds of both the shafts become same. We indicate these points by E. So speeds are equal at E, and this happens 4 times in one revolution. Now next is the speed fluctuation of driven shaft, because speed of driven shaft is varying, so it will have some minimum maximum speeds. We have seen that the equations for minimum maximum speed of driven shaft. We can say that the speed of driven shaft fluctuates between its maximum and minimum values. So fluctuation Q can be defined as maximum speed of driven shaft minus the minimum speed of driven shaft. Now let us substitute the value of N2 max and N2 minimum in this equation. So N2 max is N1 upon cos of alpha, and N2 minimum is N1 into cos of alpha. So taking N1 outside, we get fluctuation of speed Q is equals to N1 into the bracket 1 minus cos square alpha upon cos of alpha, where N1 is the speed of input shaft, which is constant, and alpha is the angle of inclination between both the shaft. Angle of inclination between both the shafts, which is constant. Alpha is constant, N1 is also constant. So Q is equals to N1 1 minus cos square alpha upon cos of alpha gives the speed fluctuation of driven shaft. Now angular acceleration of driven shaft, since the speed of driven shaft is changing, it will have some acceleration, which is defined by this equation. Alpha 2 is equals to minus omega 1 square cos of alpha into sin square alpha into sin of twice theta divided by 1 minus sin square alpha cos square theta whole bracket square. And the condition for maximum acceleration is cos of twice theta is equals to 2 sin square alpha upon 2 minus sine square alpha. Now let us have a look at double Hooke's joint. In case of double Hooke's joint, intermediate shaft is used to connect input and output shafts. Alpha is the inclination of input shaft with the intermediate shaft. This alpha is also the inclination of output shaft with the intermediate shaft. Omega 1 is the speed of input shaft, omega 2 the speed of output shaft, and gamma is the angular displacement of intermediate shaft. The double Hooke's joint can be used to connect parallel as well as intersecting axis shafts, and it can give constant angular velocity ratio. Unlike the single Hooke joint, which was used to connect non-parallel and intersecting axis shafts, double Hooke's joint can be used to connect parallel as well as intersecting axis shafts. In the single Hooke joint, velocity ratio was not uniform because the speed of output shaft was varying. Omega 2 was varying. But in case of output shaft, under some situations, we can obtain constant angular velocity ratio. Now, for constant angular velocity ratio in double Hooke's joint, these two conditions are to be followed. Number one, angle of inclination of input and output shafts. Angle of inclination of input and output shafts with an intermediate shaft must be equal. That is, angle of inclination of input and the output shafts with the intermediate shaft should be same. Alpha should be same for both the shafts. And second condition is that force of intermediate shaft must lie in the same plane. This force of intermediate shaft must lie in the same plane. So if these two conditions are satisfied, we can obtain constant angular velocity ratio for double Hooke's joint. Now these are the relationship between the displacements of input and output shafts and the intermediate shaft. Tan of theta equals to cos of alpha times the tan of gamma, where theta is the angular displacement of input shaft, alpha is the angle of inclination between both the shafts, and gamma is the angular displacement of intermediate shaft. Phi is the angular displacement of output shaft, which is equals to cos of alpha times tan of gamma. So these two equations define the displacement relationships between input, output and intermediate shafts. Now if the force of intermediate shafts are not in the same plane, we will not get constant angular velocity ratio, and hence the velocity of output shaft, that is omega 2, will vary between maximum and minimum speeds. Under such conditions, maximum speed of output shaft will be equals to n1 upon cos square alpha, where n1 is the speed of input shaft and alpha is the angle of inclination. And minimum speed of driven shaft will be equals to n1 into cos square alpha. Now let us solve some numericals on Hooke's joint. Numerical number 1, two shafts are connected by Hooke's joint. The driving shaft revolves uniformly at 1200 rpm. The angle between the shafts is 15 degree. What is maximum and minimum speeds of the driven shaft? Now, angle of inclination between the input and output shaft is 15 degrees. That is, alpha equals to 15 degrees. We indicate angle of inclination between both the shafts by alpha. Now, the driving shaft revolves uniformly at 1200 rpm. We indicate speed of input shaft or driving shaft by n1. So n1 is equals to 1200 rpm. We have to determine the maximum and minimum speeds of the driven shaft. So n2 max and n2 minimum are to be determined. We know that n2 max or maximum speed of driven shaft is equals to speed of driving shaft divided by cos of alpha. So substituting the values, we get n2 max. N2 max equals to n1 is 1200 and alpha is 15. So 1200 divided by cos of 15 is 1242 rpm. So maximum speed of driven shaft is 1242.331 rpm. N2 minimum speed of driven shaft is given by this equation. N2 minimum equals to N1 speed of input shaft into cos of alpha. So substituting the values, N1 is 1200, alpha is 15, so we get N2 minimum as 1159.1 rpm. Example number 2, angle between two shafts connected by a Hooke's joint is 25 degrees. If driving shaft is rotating at 1000 rpm, then what is minimum and maximum speed of driven shafts? Shaft angle between two shafts connected by Hooke's joint is 25 degrees. So alpha is given as 25 degrees. Driving shaft speed is 1000 rpm, so N1 is 1000 rpm. What is the minimum and maximum speeds of driven shafts? Again, we have to find out N2 max and N2 minimum. We know that N2 max equals to N1 upon cos of alpha. So we'll substitute the value of N1 and alpha. N1 is 1000, alpha is 25, so we get N2 max as 1103.4 rpm. Next, for N2 minimum, which is equals to N1 into cos of alpha. N1 is 1000, alpha is 25. So by solving this 1000 into cos of 25, we get N2 minimum, which is equals to 906.31 rpm. Example number 3. The angle between the axis of two shafts connected by Hooke's joint is 20 degrees. What is the angle turned by the driven shaft when velocity ratio is unity? Now, angle of inclination between input and output shaft is 25 degrees. So alpha equals to 25. We have to determine the angle turned by the driving shaft. That is the values of theta, for which velocity ratio is 1. So we have to determine theta for velocity ratio is 1. So we know that for equal speeds, values of theta can be determined using this equation. Tan of theta equals to plus minus root of cos of alpha. So we know alpha is 25. So by substituting the value of alpha as 25, we get tan of theta equals to plus minus 0.9520. So theta equals to tan inverse plus 0.9520 and theta equals to tan inverse minus 0.9520. By solving this, we get theta is 43.59 degrees, and by solving this, we get theta equals to 316.408 degrees. But we have seen that theta must have 4 values, because during one revolution, speeds of both the shafts become same 4 times. So these are the values, 2 values of theta at which the speeds are same for both the shafts. So we'll determine other 2 values of theta from these known values. That is called theta 1 as 43.59 and theta 4 as 316.408. This is theta 1, which is 43.59, and this is theta 4, which is 316.408. Now from theta 1 we can find out theta 3. So theta 3 equals to theta 1 plus this angle 180 degrees. So theta 3 equals to theta 1 plus 180 degrees, which is equals to 223.59. Now from theta 4 we can get the value of theta 2. Theta 4 is this much. So theta 4 minus 180 will give theta 2. So theta 2 equals to theta 4 minus 180 is 136.408. So theta 1 is 43.59, theta 2 is 136, theta 3 is 223, and theta 4 is 316.408. These are the values of angular displacement of input shaft for which the values of the speeds of both the shafts are same. Now numerical number 4. This is for double Hooke's joint, which is used to connect two shafts in the same plane, and the intermediate shaft is inclined at an angle of 20 degrees to both the shafts. Driving shaft speed is 250 rpm, and we have to determine maximum and minimum speed of driven shaft. So alpha is given as 20 degrees. Alpha is the angle of inclination of intermediate shaft with the input and output shafts. Speed of the driving shaft is 250 rpm. We have to determine maximum speed of output shaft, which is equals to n1 upon cos square alpha. So we'll substitute the values. N1 equals to 250. Speed of input shaft is given. Alpha is 20. So 250 divided by cos square 20 is 283.12 rpm. So this is the maximum speed of output shaft. Minimum speed of output shaft in case of double Hooke's joint is equals to n1 into cos square alpha. So by substituting the values, n1 equals to 250 and alpha equals to 20, we get minimum speed of output shaft as 220.75 rpm. Example number 5. Hooke's joint connects two non-parallel intersecting shafts. Driving shaft rotates uniformly and the driven shaft speed variation is within 15% of the mean speed. Maximum possible inclination of the shafts is, or maximum possible inclination between the shafts is. So we have Q equals to 15% of the mean speed. Speed variation of output shaft is 15% of its mean speed. So Q is equals to 15% of mean speed of output shaft. This is equals to 15% of speed of input shaft, because we know that N2 minimum is equals to N1. Mean speed of output shaft, that is N2 minimum, is equals to the speed of input shaft, because even though the output shaft rotates with non-uniform speed, both the shafts complete one revolution in same amount of time. Speed of input shaft is constant, but the speed of output shaft is varying, but both the shafts complete one revolution in same amount of time. That means average speed of output shaft is equals to the speed of input shaft. So Q equals to 15% of N1. Now fluctuation of speed is given by this equation, N2 max minus N2 minimum equals to, we know that N2 max is N1 upon cos of alpha and N2 minimum is N1 into cos of alpha. So Q is equals to N1 into the bracket 1 upon cos of alpha minus cos of alpha. This is equals to N1 1 minus cos square alpha upon cos of alpha. Now Q, fluctuation of speed, is given as 15% of N1. So 0.15 times the N1 is equals to N1 in bracket 1 minus cos square alpha upon cos of alpha. This N1 will eliminate this N1. So simplifying this equation further, we get a quadratic equation in cos of alpha. So cos square alpha plus 0.15 cos of alpha minus 1 is equals to 0. So this equation is of the form ax square plus bx plus c is equals to 0. By solving this quadratic equation, we get the value of cos of alpha, and from cos of alpha we can determine the alpha, which is equals to 22.03 degrees. Thank you.